Okay, welcome everybody. So today what we're going to be discussing is covalent bond energies. And so we're going to figure out how to calculate the energy change of a reaction using the bond energies, the energies of the bonds broken and formed during the chemical reaction. And it's important to know that we are dealing with covalent bonds here. Remember that covalent compounds are generally bonds between nonmetals, elements with similar electronegativities on the periodic table, that share pairs of electrons, okay? And so first off, what is covalent bond energy? It is the average amount of energy required to break a bond between elements, and it's generally going to be nonmetals if we're dealing with covalent bonds, okay? Bond energies are measured experimentally. And so experiments have been done and these bond energies have been calculated, and generally we can find them in data tables, okay? Using bond energies, the energy change that occurs during a chemical reaction, which if you guys remember back to Chem 1 was delta H, and that is known as enthalpy, that can be calculated, okay? And so here's what we know. When we're looking at bond energy, there is an indirectly proportional relationship between bond length and bond energy. So indirectly or inversely proportional relationships mean that these things are going to go in opposite directions. As the bond length increases, the bond energy decreases. There we go. And vice versa, if the bond length decreases, then the bond energies increase. Okay. So it's also important to understand that there's an indirectly proportional relationship between the number of shared pairs of electrons and bond length. Okay, so if they share a single pair of electrons, that is represented as a single line, and that is known as a single bond. If there are two pairs of electrons between atoms, it's going to be represented with two lines, and that is a double bond. And then if there are three pairs of electrons, it's going to be three lines in between the atoms, and that's a triple bond. And notice that as we go from single to double to triple bond, we have increasing bond energy and decreasing bond length. So the triple bond would actually be shorter. There'd be less distance between the nuclei of those two atoms than if there was a single bond between those atoms, okay? And so in a chemical reaction, the bonds between elements in the reactants are broken. So our old compounds, the reactants, we break them apart. And new bonds form between elements in the products. And so the deal is, it requires energy to break bonds. And so the energy of the reactants is going to be positive. And if we take away the energy it takes, or that is released whenever those new bonds form in the products, then we can find the enthalpy of the reaction. Okay, so we need to find, and this is a sum right here. This is a sigma, and that sigma represents a sum. So we're going to find the sum of every bond in the reactants, and then we are going to subtract the energy of every bond in the products. And on this page there's an example, and you're going to find several problems like this in your book and also in your worksheet, okay? So we're given this equation, and it says to calculate the enthalpy change of the following reaction using bond energies. So we're trying to find delta H. And so I have my reactants and my products. If I look at the reactants, I've got CH4. And so we're just going to assume that this is going to be a single bond. on your worksheet, since we have not reviewed Lewis dot structures yet, it will tell you, you'll actually see a double bond or a triple bond if there is one. Otherwise, assume that it's a single bond. Okay, so there's a single bond between carbon and each of the hydrogens in that molecule. There are 2 chlorine atoms, so I've got chlorine stuck to chlorine twice. And 2 fluorine, so fluorine stuck to fluorine twice. And then on the product side, okay, we've got CF2Cl2. So I'm going to put carbon in the middle because that's usually where it goes. Fluorine, fluorine, chlorine, chlorine, and it really doesn't matter the position. But this would be the molecule. So there should be a single bond between carbon and chlorine and carbon and fluorine, okay? And then you have 2HF. So H bonded to F twice, and 2HCl. So H bonded to Cl twice. There we go. Okay. And so what we have to do is we have to look up the bond energy for each bond in the molecules, in the reactants, and the products. So if I look at this one, we can actually simplify this a little bit. We have a carbon to hydrogen bond 4 times. We have carbon to hydrogen here, 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 here. And since bond energies are averages, we can assume that the average is going to be the same for all 4 of those bonds. If we look it up in a data table, which I've got some of the values down here. Carbon to hydrogen has an average bond energy of 413 kilojoules per mole. Well, I've got 4 carbon to hydrogen bonds, so that's going to be 4 times 413. Okay? Plus 2 chlorine to chlorine bonds. So if I look down here, chlorine to chlorine, that's 239 kilojoules per mole. Move this up a little bit so you guys can see it, okay? And so if I have that twice, if I have chlorine to chlorine here and chlorine to chlorine again, I'm going to take the amount for the chlorine to chlorine bond and double it. Okay? And then I'm going to add the bond energies for the fluorine molecule. So I have a fluorine to fluorine bond here and here, so there's 2 fluorine to fluorine bonds. It's 154 each. Okay? So this is the sum of my reactants. I need to take that and subtract the sum of the products. Now if I look here at this molecule, I have a carbon to chlorine bond twice, and I have a carbon to fluorine bond twice. So I have to represent that. So 2 carbon to chlorine bonds. If I look here, that's 339. Plus 2 carbon to fluorine bonds. That's 485. We have 2 hydrogen to fluorine bonds. And then we have 2 hydrogen to chlorine bonds. And so this is going to be the sum of my products. And so in the calculator, we could simply put this in minus this right here. Okay? So if I do that in the calculator real quick, start typing everything in. Here we go. 4 times 413 plus 2 times 239 plus 2 times 154. Okay, and I put parentheses at the beginning and at the end, so you'll notice the double parentheses there. Okay, subtract, and then again, double parentheses, 2 times 339 plus 2 times 485 plus 2 times 565 plus 2 times 427. And since that's the end, I'm going to put double parentheses there. There we go. And so the value that I got was negative 1,194. And the unit for all of these was kilojoules per mole. Okay? So for every mole of CH4 that goes through this process, negative 1,194 kilojoules is going to be released. So that makes this an exothermic reaction, right? We have a negative enthalpy value into the surroundings, okay?